Okay, in part 2 of our properties of exponents and radicals, I want to continue. I feel like I just kind of squeezed in an example of dividing on there, and everything ended up having to be rationalized, and sometimes that does happen and is perfectly fine, but I do want to give you another example to kind of follow along with our unit and the practice problems that you'll be doing in class. So let's look at another example, and then we'll also be adding or including adding, subtracting radicals in this video. So let's say I have square root 7x to the 5th power over 28x. Okay, so again, you can split these up if it makes, I like to do that. I don't like to work under one big radical sign. But I'm going to go ahead and expand this out as well, because I know x to the 5th power is expanded out like this. And again, like I said in my previous videos, you're going to get to where you're going to just know, okay, 5 divided by 2 is 3. So I'm going to have 3 x's leave the group with 2 x's as my remainder. Okay, and you might already be at that point right now, which is perfectly fine. And then the square root of 28, use my factor tree here, would be 4 and 7. Circle my primes. I get 2 times 2 times 7 with 1x. Okay, remember our invisible math, right? If there's not a number sitting there in the index spot, it is an invisible 2. So I'm looking for groups of 2. I assumed that you already knew that, didn't I? Up here. So always look, if there's not a number, it's our invisible 2. So we're looking for things that have been repeated twice, and those get to leave the radical. That I did not leave room for, did I? Please do that. So I get x squared gets to leave the radical, leaving behind a 7x underneath, over a 2 gets to leave this radical with a square root 7x underneath as well. Okay, so again, if you look at your radicals kind of like exponents, or not exponents, oh goodness, I'm going to keep saying it wrong. Let me try it again. If we look at our radicals as variables, right? Well, I'm not changing what you already know. Anything divided by itself, we can cancel and say it's 1. So if there was nothing here, I would put 1. Since there is a number outside or terms outside, I will simply write those down. Cannot be simplified any further. I don't have a negative exponent, so I'm good to go. Okay, let's look at another example of dividing. So x squared y over 256. Again, there's not a number sitting in the index spot on that little edge, so it is an invisible 2. Okay, I'm going to go ahead and split these up. So I'm just focus on the numerator, and then I'll just focus on the numerator, or the denominator. Goodness. Okay, well, it's invisible 2. This x is already squared. We know 2 divided by 2 is 1. So 1x gets to leave the radical while the y must stay behind. Over 256 using my factor tree, 2 and 128, which is 2 and 64, 2 and 32. You notice I like 2's, right? Just halving my numbers. It's easier to do that in my head. You feel free. You can use any prime factors you want. And like right here, if you don't know a prime, just use any factor pair that you know. Just remember, don't use 1. 1 is not prime or composite. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to have 8 2's underneath here. I'm going to go ahead and write it like this. I'm going to have 2 to the 8th power. Remember, looking for groups of 2. Well, 8 divided by 2 is 4. So what I'm left with is x square root y over 2 to the 4th power And if you want, if you feel better, expand it out. Do whatever is you're most comfortable with. 2 to the 4th power is 16. Okay, let's look at multiplying. Multiplying radicals. Okay. If I have the cubed root of z times the 5th root of z times the 10th root of z to the 3rd power. Okay, so you'll see they're getting a little bit more complicated. What I'm not liking here is I don't have the same index. So I just don't feel like I can just multiply z times z times z to the 3rd power, right? And you're exactly right, but what we can do is go ahead and change these to exponents because we can multiply fractions and exponents that aren't the same, right? So I'm going to go ahead and squeeze my invisible ones in there because if I don't, it's something in my brain, I won't see it. So I'd have z to the 1/3 power times z to the 1/5 power times z to the 3/10 power. Now I can multiply when my bases are the same, and I'm just going to multiply straight across. Oh, no, I'm not. Goodness, I better write it. When our bases are the same and we're multiplying, what do we do to our exponents? We add them. I think it's time to go home. I keep making mistakes here. So it's going to be 1/3 plus 1/5 plus 3/10. Okay, now a side note here, to be able to add and subtract exponents, we must have the least common denominator, right? Or at least a common denominator. Well, what's the least common multiple of 3, 5, and 10? Or you can always just multiply 3, 5, 10. It's going to be 30. It's the smallest one I can think of because 10, 20, 30. So I am going to multiply this one by 5, this one by, no I'm not, 10. 5 times 6, and 10 times 3. Whew, I need to slow down because I'm going to make a silly mistake. I just know it. Okay, 3 times 10 is 30, 5 times 6 is 30, and 10 times 3 is 30. Okay, here we go. So I get 10 plus 6 plus 9, which is 25 over 30. And I can reduce this to 5 over 6, reducing by 5. So what I have here is z to the 5 over 6 power. And I know you're looking at this like, this is a crazy rabbit hole I'm going down, right? Well, my goal is to eventually get it back to radical form. Remember, we always want to answer a question the way it's been asked unless they tell us differently, like, write your answer as a decimal or in fraction form. So it hasn't told me that, so I'm going to go ahead and convert this back to radical form. Remember, it was z to the 1 over 3, so this would be z to the 5th power, and my index is 6. So 6th root of z to the 5th power. Okay, so our next example is adding and subtracting radicals. I'm still using distributive property where needed. I'm still following order of operations, so I will work this out left to right. Excuse me, since I'm adding and subtracting. But again, I want you to think of the radicals as like terms. Okay, so if your radicals are not, the same index, if they're not the same number under there, your radicand, they're not like terms. So I can't actually add and subtract these. So what I'm going to do is simplify them down to the same radicand. So I have 3 times 9, which is 3 times 3, which is 5 square root 3 times 3 times 3. And again, I keep repeating that word again, don't I? Again and again. Sorry. Index is 2, so I'm looking for a group of 2 that get to leave the radical sign. So that's 5 times 3, but the 3 is left over inside, right? This guy, he's got to stay. His ticket out from underneath the radical is he has to have a pair. Okay, same thing here, 2 times 9, 3 times 3. Here's my prime factorization, minus 2 times, 2 square root 2 times 3 times 3. Again, if there's not an index, it is an invisible 2, just like our invisible 1 exponents. Okay, don't forget our invisible math. So we get minus 2 times 3 square root 2. This loner right here has to stay. Factor this out, 2 times 6, 2 times 3. This becomes square root 2 times 2 times 3. Index is 2, so I'm looking for pairs. It means a 2 gets to leave the radical sign. Okay. Clean this up. 2 times 3 is 6. Again, still following order of operations, so I will work left to right. Well, let's combine like terms. They have to have the same index and radicand for me to be able to combine them. And look, I have 2 square root 3s. So those 2 may be combined. Remember, always take the sign in front so you know if you're adding and subtracting. So we get 17 square root 3. And my negative 6 square root 2 stays there. Okay, our next example is seeing our radicals and our exponents with our FOIL method, our over, over, under, under. So let's get started. Let's say we have 5 square root x plus 5 times 9 square root x minus 6. Again, I'm not really changing what we already know. I'm going to treat these like exponents. Not exponents, I keep saying that. I'm going to treat my radicals as variables. I'm going to have to redo this video because I keep fumbling through my words here. So I'm going to take the first term, go over to the first and the last. Okay? Just remember, everything needs to be multiplied by everything. So in my class, we like to say, start here and go over, multiply, take the second term, under, multiply, under. So here we go. 5 times 9 is 45. I'm not changing what you already know. Square root x times x is x squared. 5 times negative 6 is negative 30. Square root x. Again, I would put negative 30x, right, if I didn't have the radical. So it's not really changing up much of what you already know. 5 times 9, 45. Square root x. And 5 times negative 6 is negative 30. Okay, now I'm going to combine like terms, and I am going to simplify a little bit because I know that the square root of a square, they are inverse operations, and those two will cancel. So I'll just be left with 45x. And I have like terms right here. Let me change colors. I'm going to get a lot of pink on here. Negative 30x square root x can be combined with 45 square root x. Okay, here we go. So I get 45x here. Negative 30 plus 45 is positive 15 square root x minus 30. Okay, none of those can be combined. None of them are like terms. Okay. Well, Miss H, what if they give me a problem that has square root negative 5 minus square root 7 and it is squared? All right. Well, it's simple. You can just expand that out. And now it's like the problem above, and you would just FOIL it or over, under.